Hi everybody, my name is Llew Vaughan-Edmunds, Senior Director of Marketing at Navitas. Today I will give a quick overview of GeneSiC's MOSFET technology from 650 volts to 6.5 kV and driving innovation. So let's start with the wide bandgap total available market. As of 2026, we see projected about a $22 billion pure play market opportunity. This is just wide bandgap. So on the y-axis you can see application power, on the x-axis you can see the device voltage rating, and we're going to look at these different colors briefly. In the bottom left you see the gray, which is silicon. That still dominates today, up to about that 80 volts range. It's when we get to that 650 volts, the higher voltages, is where GaN and silicon carbide come into play, and you can see the benefits of wide bandgap. So various applications at that 650 volts are driven towards GaN, the high switching, ZVS, high power density, that kind of focuses towards GaN, whereas the rugged, higher power type applications, that leans towards SiC. And that's where that light blue area in the middle is. Depending on the application, kind of depends on the device technology you need. So you can see, I'll just pick one, which is a popular one, the EV, the 400 volt battery for the OBC, where you can switch at ZVS, and it's all about power density. You can use, and people are using GaN. Whereas for the traction inverter, it's more rugged, it's more higher power. You need short circuit rating. That is going towards silicon carbide. And there's all those trade-offs between the GaN and SiC and between those two, and that's fine. Now it's when you get to the 1200 volts onwards to 6.5 kV, this is where the higher power, more rugged requirement for and also thermal conductivity is needed to distribute that heat faster and quicker. And this is where silicon carbide wins, because it is a vertical device. The material of silicon carbide has a high thermal conductivity, and it is more rugged. So what we're seeing now is those applications which are going to higher voltages, for example, like again the EV going to 800 volt bus, you need a 1200 volt device for that. That's where silicon carbide would be a better performing device versus GaN, because GaN is lateral, it'll be a larger die, it's got a silicon substrate, so the power requirements are different. So silicon carbide will win. When it goes to the 3.3, the 1700 volt bus, the 3.3 kV, the 6.5 kV, this is really a very interesting place for silicon carbide when it competes with silicon IGBTs. And we can talk about that more on the next slides. And that's where GeneSiC silicon carbide technology really shines through. So GeneSiC has been around since 2004, and they came in from the high voltage aspect, where quality, reliability, and ruggedness have been key requirements for those applications. And what we need to see now is, and I'll go around the circle briefly and we'll follow up with more slides, is that we have a range of voltage classes up to 6.5 kV. We have the widest range of voltage classes. With our device structure, which I'll talk about in the next slide, we operate cooler than competition. I'll talk about that a little bit more. The withstand short circuit rating is key for those motor drive applications and industrial applications which need that ruggedness. Alongside that, for paralleling, in order to parallel multiple die, you need a stable and a tight VTH, and that's something we have focused on. And then next to that, the avalanche tested, we do 100% tested for avalanche, and we go to an extra level of avalanche rating, which I'll talk about. And the last one is the fast switching. So we designed the FETs to have a fast switching figure of merit. in the device technology itself, which we can touch on. So one of GeneSic's key differentiators is its leadership in technology. GeneSic's been around for almost 20 years, and it's been solely focused on silicon carbide. It's in the multiple generations now, and it has been focused on quality, performance, and reliability. And you can see this play out here. So if we look at the three different device structures, you can see planar on the left, trench in the middle, and GeneSic's approach on the right. And we split it by manufacturability, performance, and reliability. So if we just have a quick scan on all of them, planar, it's been around for a few years. The manufacturing is repeatable, it's high yield, it's relatively low cost. From a performance standpoint, it's a planar gate, so you don't have that current density. The switching is slightly slower than trench naturally, and the RDS shift versus temperature is quite high. From a reliability point, it's better because of the planar gate. The gate oxide going on top of it is more stable, and you get let's say a more stable threshold voltage. Going to trench. Now trench today it's hard to etch. You have micro etching. The different sidewalls etch at different rates, so it's tricky to do the etching as of today. Therefore, that results in lower yields and higher cost. From a performance standpoint, yeah, you have the lower RDS on per area, you have faster switching, but also you have a high temperature spread with RDS on. From a reliability point, the failures due to the gate oxide, laying down gate oxide on a trench surface is tricky, and this non-uniformity can affect the threshold voltage shifts, and additional to that you have a lower short circuit capability. So GeneSic's approach, it plays on the planar gate, but it has some structural and technology differences which shines through. So it has the manufacturability of planar, it has the performance which is at the level of trench, you could say, and it has that reliability which is above actually planar through some of the device concepts and technologies we've integrated in the design. And you can see here on the table we've listed GeneSiC alongside 4 different competitors. Now we're looking at the figure of merit, so you can see the resistance. Now if you look at resistance at 25 degrees C, you can see they're all around about 40 milliohms. Now look at it at 175, you see that shift going to almost double on one of the devices. That's where GeneSiC pulls it in and keeps it as tight as possible. And that's one of the key things in a real application when you're switching at elevated temperatures. You know, it's not at the room temperature what you're really testing at. So that's one of the key things we looked at. Also the energy losses. We're looking at the hard switching versus soft switching, and we're trying to focus on those markets where switching at higher frequencies is key. So if you can see the figure of merit there of the hard switching, we're significantly better than the competition, and the soft switching, yeah, you know, we're in line at the, and if not just better. So the key message is here that when you have a lower power losses at the higher temp, higher speed, you get that higher efficiency and the energy savings which the customer requires. So this is targeted for real life applications. We performed a real life test with GeneSiC versus competition. You can see on the right. And this is the same equivalent switching with the gate, the same switching speed, the same PCB, everything's the same, and we've done the comparison. And you can see GeneSiC operates over 25 degrees cooler than the competition. And you can see the reason why is that we've designed the device so the RDS on versus temperature spread or variation is reduced in comparison to the competition MOSFETs. Now, we do it just at the level where it's perfect for paralleling, but also at the level where you can see the most performance efficiency. I'll quickly touch on one of our other technologies where we integrate the Schottky diode monolithically onto the silicon carbide MOSFET. And there's a reason for that. It's for the third quadrant operation where the VF is quite high normally, and also potentially bipolar degradation. What we do is eliminate all of that by integrating this diode contact, where your VF will significantly reduce, your reliability will increase, and this is perfect for those applications and motor drives and higher performance, higher efficiency requirements. And this right now is on our 6.5 kV technology. We're going to bring this down into the different voltage classes. As mentioned before, GeneSiC is very focused on highest quality and the highest reliability. We do 100% testing on avalanche. We show data results which show us to be about 3 times stronger than competition. For paralleling, that's key for us for die cells and for modules, where the stability, or let's say the variation of threshold voltage, has to be very tight. From die to die, wafer to wafer, lot to lot, but also from versus temperature. And that's something we have focused a lot on. And the last one's the short circuit withstand time. We see ourselves about 30% longer than best in class. This is key for those high power, rugged requirements such as motor drives, or where a short can be observed and they need to be, switched off. On top of that, we have 0 reported GeneSiC related field failures. So we're very proud of that statement, and I think that reflects in the technology that we're showcasing. Looking at our MOSFET portfolio, we offer the most comprehensive silicon carbide MOSFET portfolio throughout the voltage classes. So we have everything from 650 volts to 6.5 kV. We have, I think, the largest portfolio is 1700 volts and also 3.3. So we really offer everything across that spectrum where silicon carbide really shines through. Okay, last slide to summarize the presentation. So GeneSiC is a pioneer in silicon carbide technology, heavily focused on performance, quality, and reliability. We have these leading edge technologies such as trench-assisted planar gate and the monolithic MOSFET diode, which enable new levels of system efficiency and reliability to our customers. The device technology has been tailored to offer the highest performance in real-life applications. Quality, robustness, reliability, that's the heart of GeneSiC's MOSFET technology. And GeneSiC offers the most comprehensive MOSFET portfolio in the industry. Okay. Thank you very much for listening, and if you have any questions, please feel free to contact me. Bye.